Welcome back. Having introduced a simple phenomenological rate law involving a single radioactive decay constant in the previous lecture, we will go into slightly more complicated cases. These are all fairly realistic cases because most of the radioactive elements are not present in a pure form. So when you have an impure form of radioactive material, you may have more than one pathway that is possible, resulting from more than one radioactive element, or even in the simplest cases, each radioactive element may decay via more than one mode, right? So when we had in the previous lecture, we had only one lambda, but actually you can have more than one radioactive constant, decay constant, depending on the pathway it chooses to decay. For example, californium can display spontaneous fission and alpha decay, right? So we will come into uh, many such cases in as we progress along this course. So this is a simple example. So let's say this is California. It may decay via spontaneous fission by in one pathway, and it can decay by alpha decay by a different pathway. And because the energetics is different, that is to go from here via to a product involving spontaneous fission or to products involving alpha decay, the energetics are different. Therefore, kinetics will also be different. As I've stressed many times in the previous lectures, kinetics is representative or it can be correlated to underlying energetics. If the underlying energetics, that is the difference between the products and the reactants, is different in this case and different compared to this case, because the energetics is different, the kinetics and is also different because the activation barriers involved will be different. So how do you represent this law? What is the form of the law? Okay, this is sort of obvious. You can think that lambda is an additive constant, right? Because this, the assumption here is this is sort of independent of this. Okay, so that is an assumption, but that's a reasonably good assumption. Now, why is it reasonably good? Because you will see in when you do the experiments, that's the way many of the systems behave. So once you have this thing, so you rate of change of radioactive elements with time is proportional to n, and you can write it in this manner. Okay. So because lambda is connected to t half, you can associate two different t halves corresponding to two different lambdas. Corresponding to lambda 1, we have this. Corresponding to lambda 2, we have this. So you can write such a formula. And with this formula, you can get the t half when the material uh, decays via both the pathway, right? You cannot really, in this case, you cannot, in many cases, you cannot suppress one pathway completely. So the material will decay via both the process, and the T half of such a decay process involving two different pathways is given by this formula. It's a fairly straightforward relationship to um, derive. So it's intuitively obvious that because lambda is lambda 1 plus lambda 2, the half-life of the material, this is always less than the half-life of these two quantities, right? So if it can decay um, by more than one mole, then the propensity to decay is increased when you add the number of modes. Therefore, this statement is true. Let's try to look at it more in an intuitive manner. So here what is stated is for californium, the T half for spontaneous fission is 84 years, and T half for decay, for alpha decay, is 2.85 years. This itself tells something. Okay, what does it suggest? Let's just imagine a nucleus, let's say californium. So if you want to emit an alpha particle, you may think that an alpha particle should be formed within the nucleus, close to the surface of the nucleus, right? So to begin with, let's say you have uh, many protons in californium, and all the protons are more or less uniformly distributed in the nucleus. And within the nucleus, there are fluctuations in the structure. In one such fluctuation, let's say you form an alpha particle inside the nucleus, close to the surface. There is a substructure, if I may use that word, wherein 2 protons and 4 neutrons are localized in the nucleus. Not only localized, you form a distortion away from a spherical structure, wherein there is a projection involving something like an alpha particle. Okay, so consider the chances of that substructure occurring compared to a substructure involving two atoms, two nucleus that are formed via spontaneous fission. Okay, so this is one would imagine that this fluctuation, okay, internal fluctuation, okay, is much more easier to occur compared to the fluctuations involving spontaneous fission. Because these fluctuations are more easier, the radiation decay constant, that is, let's say lambda corresponding to this would be larger compared to lambda corresponding to this. Correspondingly, T half of this will be lesser compared to T half via this particular pathway. So what I'm asking you to build is, instead of looking at the nucleus as some structureless quantity, okay, some structureless object, okay, that's the way we have been thinking about a nucleus from high school, right? As nucleus is some spherical structure, we have to start thinking about the nucleus in terms of some substructures, okay, and some fluctuations. This will give us a better intuition to start thinking about radioactivity per se, and especially about the different radioactive decay processes. What makes alpha decay different from spontaneous fission, different from beta decay, and so on. Okay, so start thinking about it in a more microscopic manner. Okay, in terms of the nucleons uh, inside the nucleus. So again, coming back, if because these two T halves are this much, the T half is less than the smallest T half, right? Because even compared to spontaneous alpha decay, because there is an additional mode, spontaneous fission, your T half is further decreased. This is one way mathematically you can see this from this formula, but also intuitively you can anticipate that the overall T half will be less than the T half of either of the pathways. So what is also seen is that if you have a radioactive mixture, I mean, if you have a radioactive compound decaying via more than one process, you plot the activity. Total activity is plotted here, and total activity is comprised of different subcomponents, right? You can decompose uh, in terms of different radioactive constants. This one involving lambda 1, other involving lambda 2, and so on. And when you do that, this is the overall activity change. right? So the activity, overall activity decreases. When you plot it in the log scale, what it tells you is the slopes when plotted. Note this y-axis is along the log scale. The slopes are indicative of uh, lambdas. Okay, so B and C correspond to two different decay constants. In this mode, it decays much faster. Um, TF is lesser, and this mode has greater lambda. In this mode, um, the TF is longer and lambda is lesser. So if the overall activity is known via certain procedures, you can get the individual decay constant. Once you have the individual decay constants, you can also get the t half, right? So if you plot in log scale, when we first looked at t half formula, we clearly interpreted uh, the decrease in radioactivity going from 2000 to 100, and so on, right? All these things will give you an indication of what is the t half corresponding to either of the pathways. So this is all very, very realistic because that's the way nature behaves. That is, it is not just one pathway that is uh, um, active, but typically the radioactivity may occur via more than one pathway. In in the next lecture, we'll take up a different topic. We talked about decay, but as you might have seen in your chemical kinetics or chemical reaction engineering classes, there is not only kinetics, the kinetics might lead to some kind of an equilibria. Okay, so we'll clarify the here nuclear equilibria is slightly different from what you've seen in your chemical reaction engineering or chemical kinetics class. We will take this up and we'll introduce an important formula. We won't derive it. That formula is called Bateman equation. This you would see often in radioactive literature. These topics will be taken up in the next lecture. Thank you.